Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
My pleasure to introduce Tom Nielsen, who just out of the blue got in touch with me a few months ago via a roundabout route because he'd seen some of our videos to do with our tool distribution modeler on YouTube or on the web somewhere. And then we had a really nice chat a couple of weeks ago, and I was really struck by kind of what a multifaceted, interesting sort of person Tom is. And actually the brief chat we've had this morning has only reinforced that. So I didn't realise, for example, that he was here at Cambridge as an undergrad. He started off doing maths in his first year, almost instantly switched to engineering, got a bit bored with that, switched to philosophy for his second year, got a bit bored with that and switched to psychology in his third year. He then went off to do a PhD in computational neuroscience, a couple of postdocs, including Harvard Medical School and no doubt somewhere else interesting, before he decided to go entrepreneurial and develop some software which is called Bayesian to do with probabilistic programming, Bayesian statistics and predictive modeling and all that kind of stuff. So he's kind of a bit of a rare breed, I think, Tom, if you don't mind me saying. So anyway, so that's why I thought it was worth inviting Tom here. So without further ado, I'll let you get on with the talk, Tom. So thanks for coming.
Thanks, Drew, and thanks for coming. I hope not to waste your time. I'm going to talk about some work we've done in designing a probabilistic programming language that's really built for practical use for data analysis. Before I get into that, I want to talk a little bit about a hidden assumption in data analysis or data processing. And so what I really mean by data analysis is that you start off over here on the left with some data that you've observed. So this can be in a variety of scenarios. In science, the data may come from a telescope or a microscope or from an amplifier. Or in retail, this may be everything that you've sold. Or in finance, we have a lot of historical pricing data. But really, you want to get over here. And maybe you want some sort of insight out of your data. You maybe want to measure some constants or some ratios. Or maybe you just want to take a decision. You want to ask, this is my data. What should I do next? Should I buy this? Should I sell this? What price should I buy it at? Or maybe you want to calculate a risk. What's the risk that we're going to be bust in 6 months? Or you may want to predict something about the future or about some new case about which you have incomplete information. And so now the hidden assumption in much of data processing is that the way we do this is by setting up some sort of transformational pipeline, some sort of computational pipeline. So you might start, say this is some amplifier data, you might start off by filtering it with a Bessel filter or Butterworth filter, and then you might do a fast Fourier transform, and then you might want to look at that power spectrum, and you may want to measure how high and how wide some of those peaks are, and then finally you've got a bunch of numbers that you can stick into a statistical test, maybe a t-test. So really what you're doing is reducing complex data to a handful of numbers that you can interpret. And I think this is very natural to us, and I think most people do this without really thinking about it. But there are some problems with this paradigm. And so the first one is that I don't know which one of all of those possibilities I should choose. Should I choose a Bessel or Butterworth filter? Which corner frequency should I use? And when I come to measuring, how should I exactly measure these peaks in the spectrum? And which statistical test should I use? And I don't think we really have a good way of choosing these computational procedures, other than that this is something you're meant to learn through some sort of apprenticeship, through the elders, which is the same as saying that we really don't know. But this is a particular problem in data analysis. When we have a arbitrarily set conventional threshold for what is deemed publishable, that is the 5% significance level. Because there is a flexibility in these parameters. I can change the corner frequency of my filter, and I will get a different response at the end, a different final score. And so if I don't get the results that I like, I can just choose some different parameters, and I can try again, and eventually I might find something that is deemed publishable. And this sounds awful, but this is something that people do. So, sorry, this didn't come out well, but there's a paper here which shows that undisclosed flexibility allows you to present anything as significant. And there is lots of evidence that in industry research, where you have to reach some threshold for approval, for efficiency, for instance, for drugs or medical devices, this kind of flexibility is widely abused. Now, so the second problem here is that as computational scientists, we love to write models. And what these models do is they go from some parameters, and using a computational procedure, they generate fake data. And if you can do this well, I think that shows a lot, that you know a lot about the underlying system, if you can do a faithful simulation. And yet, this picture has no place in that transformational pipeline. They're completely separate activities. Of course, you can analyze the simulated data and see whether these parameters that you used can come out at the other end, but there's no real principled way to do this in general, which is a shame. And so this third problem, which is really the most serious, is that it is really difficult in this view to propagate uncertainty correctly. So the raw data has its own variability and noise, and that means that the final numbers that come out at the other end should really have some kind of uncertainty, some kind of error bar. And to do that is really difficult. You need to take the partial derivative of each transformation, and that's really hard, right? So what's the partial derivative of the Fourier transform with respect to one of the corner frequency of the filter that you use? That's really hard, and people end up not doing it in practice. So you end up not having that uncertainty, or you end up at least dropping the uncertainty from the earlier stages of the data analysis process. So you might ask, is there an alternative to this view? Is it possible to do data analysis in a different way? And yes, it is. So there is an alternative. It is probabilistic programming, and it is what I'm going to talk about for the rest of the talk. So the idea here is that at least initially, we take this idea of the model and place this on a pedestal, and all the analysis will flow through that model. And this model is somehow a mapping from the parameters to the observable data. I'm not saying it's a function. It's some other way of getting from the parameters to the data, of generating the data from the parameters. And then by virtue of working in a probabilistic programming environment, we have a procedure or some way of inverting that process. So we can flip this arrow, and we can somehow go from the observable data to the parameters. And so we can learn what the underlying state of this model is, giving the data that we have actually observed, the real data. And so I think it's important not to stop here and consider everything else that you can also do. So based on these parameters that you have now obtained, you can now do a variety of tasks. So for instance, you can forecast the future. You can calculate the probability that something awful is going to happen. And you can take decisions if you can define a utility function. And these decisions, the outcomes, the actions chosen from this decision procedure in this way are provably optimal if you have the right model. Now, we never really know whether we have the right model. So one thing that we also want to do is to somehow figure out if this is a good or bad model. And this should also be somehow possible in a probabilistic programming environment. But there may be other things that you want to do that I can't think of. So we better make sure that these are not primitives, that these are built using primitives that you can then use to define other kinds of transformations, other ways of exploiting this parameter estimation.
Why does RISC only accept a model and not and the parameters, and not also some predicate saying what is the condition whose probability we're estimating?
Oh yeah, it does. Yeah, it does. So sorry, yes, you're absolutely right. So you want to then define some function from maybe just from the parameters to a probability, depending on exactly how you're calculating risk. Or you may actually want to predicate this risk on the future. So you may want to define it on. So different ways, there'll be different risks, and you'll calculate them in different ways. OK, so the only thing that these are actually quite easy to define. They're easy to calculate sometimes computationally. The only thing that might seem a little bit magical is this estimate operation. So you might wonder how you do that. And so actually we've known for some while how this can be done. They all depend, or at least these two methods depend on defining a likelihood function. And that is the probability of observing your data given the parameters. So if you can write some sort of expression, or maybe a function, for the probability of that data, given that these parameters are in scope and that you pretend that they have concrete values, then you can run a maximization procedure and find the actual parameters that maximizes this probability. This is a principle that you can adopt if you like. And it comes out with a set of numbers. And you might also get out some sort of uncertainty. But it is not a probability distribution. The advantage of using Bayesian inference that you do get a probability distribution over the parameters given the data. And so since our model has to be written as a probability distribution, that means you only have one kind of thing, and we know what kind of thing a probability distribution is. So that, for me, that's the chief advantage of using Bayesian inference. You get the answers as a probability distribution over the parameters given the data. But it is a little bit more complex. So it depends on an additional term, which is the prior, which is what you already know about these parameters. And so you do have to define that. And this is so complex that we usually just ignore it, which we can, fortunately. OK, so before I sell this too hard, I think we should also just think about when do you not want to do this. So you may not have a model at all. You may have some data, and you may not be in possession of a model. So you may want to do some exploratory data analysis in order to formulate a model. And then when you have a model, it may not be efficient to estimate the parameters in this way. It may be efficient, and it's very hard to predict how efficient that's going to be. However, it is unlikely that you can do this, and yet it doesn't really help you much in whatever data analysis problem you have. Very often, knowing the parameters will give you crucial information to give you whatever insight or whatever estimation or forecast you want to do based on the data or prediction. Another reason why you might not want to do this is that the technology is simply not up to scratch yet. So you can do something like this. So this is a bit of code from R, from the programming language R. And so I've got a piece of data here. This is the time series data. And I can run the ARIMA. ARIMA stands for autoregressive integrating moving average. It's a time series model against these data. And then I get the results back. And so the only things I have to type on this slide to do a forecast are these two lines. These are the only two lines of code that do something. Now I can ask what the results are, and I get a bunch of acronyms that some people know what it means. And I get some parameter estimates. That's this one, right? And then I can use that result to do a forecast. And I get then, these are the next points into the future with their confidence intervals or spreads or standard deviations or standard errors. Now, it's very nice that this is 2 lines of code, but actually that tells me that it's too short. These are black boxes, and they're not very flexible. So I cannot fit any model I like here. This is a very restricted class of models. And this forecast, I might know something about the future. I might know that something will happen, or I might think that something will happen, which is not in the historical information. I might want to incorporate that in the forecast, but there's no flexibility for doing so here. So I'm looking for something that's actually a little bit more verbose than this, that allows me a little bit more flexibility than just a black box forecast. So let's see what this RMR model is. So it has 3 kinds of terms: the autoregressive term, integrated, moving average term. I'm going to ignore the integrated and moving average term. They're a little bit more complicated, but they roughly follow the same form as this. So these numbers up here, they tell you how many terms you're allowed of each kind. So one of those is the number of autoregressive terms. And so if I have 1 autoregressive term, then what my model says is that the next value in the time series is distributed by as the number that you get by multiplying the previous time step with a parameter. This is a parameter. This is a number, a real number. And then adding a randomly chosen value. And if I get to do 2 autoregressive time steps, then I get to look 2 back, right? So this is the next time step, this is the previous one, and this is the previous one before that. I get to multiply these 2 by parameters of the model, and then draw a normally distributed error term. And so, but even when you incorporate these and the integrated moving average terms, you still have a pretty narrow, restricted model. For instance, I'm always stuck with a linear combination of terms. And I'm always stuck with this normally distributed error term, which may not be what my model is. What if I wanted to do something completely crazy? Yeah, if I wanted to say, this is really crazy, right? So the next time step is drawn from a gamma distribution, where the 2 parameters, the scale and the location parameters of this gamma distribution, are some crazy nonlinear functions of the 2 previous time steps. Yeah? If I ever wrote this on a statistics exam, I would fail. Because there probably is no process in the world that is described by this equation. I mean, it's ridiculous. But I think if we're providing software for data analysis, for modeling, you have to let the users experiment with the grotesque. And if nothing else, then they can figure out for themselves why this is wrong, if it is wrong. So
can you say again what sense it is wrong?
Well, probably this. I mean, I think you should be allowed to do this and run this against your data. But I think this is probably not going to work very well, because there will be no continuous time approximation for this time series. So it will depend heavily on your discretization of the data.
So there's no good implementation of this?
No, I'm just saying there's no process, there's no physical process out in the world that is described by this equation. Yeah, this is not a law that describes anything in society or in physics. It might be. I might be wrong, right? I think you should be allowed to find out. I think you should be allowed to enter this and find out if it is wrong.
I would have thought the fact that there's no physical process that follows this is exactly the kind of thing that statisticians don't care about.
Right.
It seems to be like that's the one thing they never ask is actually, is this model, does it correspond to anything that happens in reality?
Right, right,
So
yeah.
you're right.
There's also no physical process that implements the first 2.
That may be true as well. Okay. Now, so I think the first, or at least the first in data analysis environment that I know of that allowed you to do crazy things like this and allowed you to run any model against your data was the WinBugs software, the Bugs software. It was actually written here in Cambridge at the MRC Biostatistics unit. And so this is an implementation of that crazy model. So here I've got my gamma here. So that's the, you draw the x, the next time step is drawn from a gamma distribution. So here, the tilde means distributed as. So that means that this variable is distributed as a gamma distribution. And that relies on 2 local variables. So notice these are deterministic calculations, right? These are not probability distributions. This is just a simple equation. I should say I'm not really sure this is really valid WinBugs. In fact, I think I left out a closing parentheses here. I just typed this out. But this is roughly Winbug's implementation of that process. So these are just calculations, and they get put in these local variables, or deterministic variables, and then you use that to calculate the next step of the gamma process. And up here is your prior. Yeah. These are the distributions for your 4 parameters. And so you can really write probably any or a huge range of models in this language, because you can say that any variable is distributed according to any probability distribution. You can do any calculations you want to. Unfortunately, that's the only thing you can do. You can only describe models for data that you've observed. And so you cannot do any of the operations that I showed you before: forecasting, risk estimation, prediction, decision. You can do some of those by doing some tricks. So you can sometimes add an extra parameter that corresponds to your forecast, and you can add that in this way here. But I think what we're looking for is not a bag of tricks here that you can stretch this with a little bit more. We're looking for something that gives you much more flexibility in the kinds of models that you write. And so we have to look somewhere else for some inspiration. And that is looking at functional programming. And realizing that statistical models are monadic programs. So in functional programming, we try to calculate with functions that really are just mathematical functions. So functions here are pure mappings between 2 different sets of things. And so for any given input, you always have to get the same output. That's one way to define a pure function. So we write this f here, which is the arrows, has the type of going from the diamonds to the stars. It's the type notation for that. And so no matter how many times you look at this arrow here, you always get the same output for the same inputs. And so for instance, when you're writing a function called prompt, this is the prompt from JavaScript, for instance, that asks the user for a value, like this could be, how old are you? And this would be the user's reply. That prompt function cannot have this type, because for the same question, the user might give you 2 different answers. So the way you do that instead is to say that this prompt function takes a string, which is the user, which is displayed to the string which is displayed to the user. How old are you? But then it returns an action it returns a string, but wrapped in an input-output operation. So that you cannot, for instance, then write print hello plus prompt, what is your name? Because this is not a string. This is an input-output action, which will ultimately yield a string. So functional programmers, some of them, like to tell you that it is extremely powerful, that you cannot write this. And indeed, this can be used to some spectacular effect, because you can generalize over these, and you can write your own loops, for instance. But I think the jury is still out on whether it is always a good idea to always restrict the user to this style of programming where this is banned. But I'm going to show you that when considering statistics and probability distributions, this is a really good idea. So we define a type of probability distributions as a random number generator. That is a function that takes a seed and then yields a value of some type. And then we implement what's called the monad instance for this. And what it means to be a monad means that you define a sequencing operator, this bind here in red. And what that means is that you can draw a value from one probability distribution, and then you can send that to a function, and then you get to use the value that has been drawn from that probability distribution as if you knew exactly what it was. So inside this function, x is a number, is a real number. And so you can sequence draws from probability distributions using this operator. Let me show you how that works. So I don't know how many of you are used to looking at gamma and normal distributions. So here's some pictures of them. So the gamma distribution is sort of gives you always positive numbers, and in this case it looks like something that's likely to be small and less and less likely to be higher, a larger value. So this is a histogram of values drawn from the gamma 1-1 distribution. If you change these numbers a little bit, sometimes it can look like a bell curve here. But the gamma distribution always yields positive numbers. The normal distribution, you probably know, most of you, this has 0 mean and a variance of 1. And so this is the shape of the famous bell curve. And now, if I compose these two probability distributions in this particular way, let me say here, such that I use the x that has been drawn from a gamma distribution as the variance component of the normal distribution, then I get a histogram that looks like this. Now, this is a little bit torturous to work with. Fortunately, the functional programmers have invented a syntactic shortcut. This is syntactic sugar. And what that means is that you just basically flip this bit. So you're saying you pick a value x from gamma here, and then in the rest, inside this do block here, you get to use that x as a real value, as an actual number in the computations that follow. So this becomes a little bit more readable than this. But it really means the same. Okay, so I want to show how we can use this to build a real statistical model for a simple example. So let's pretend we are economists, and we've got some data, or actually, we want to simulate some data first for the relationship between inflation and growth. And so we want to generate these kind of points that have a steep slope. I don't actually know which way it should actually go, but we're just simulating data here. So I'm going to build up a real statistical model for this kind of data. So we're going to use this notation here. So first I'm going to pick an inflation from a uniform distribution. And then I'm going to calculate the growth from a normal distribution where the mean is calculated based on the inflation that I've just picked and the slope and an offset. This growth 0 is the intersect with the x-axis of the line that fits these data, and then there's a variance. And then I'm going to return the inflation and the growth, so I have a point. Now, return sort of in a certain way, it tells you what the output of this sequence of computations is. Some of you know that it's a little bit more complicated than that, but you can use it in that sense. You can use it to say what the output of these computations are. So this gives me a probability distribution for 1 point, because I've only picked one inflation and I've calculated one growth, picked one growth from a calculated normal distribution. So I want a probability distribution for all of these points. So for instance, I have a function called repeat, which takes a number, that's the number of repetitions, and then it takes a base probability distribution, and then it gives you a probability distribution over lists of things, right? Now this was, this base distribution here was a list over points, so I have a list over points of things here. Okay, so now I have a distribution for all of these points. Now the problem here is these parameters. There are 3 parameters: slope, the offset, and the variance. And the problem is, how are they going to come into scope, looking at it from a programming language theoretical perspective? Right here, if I ran this, then this would fail because there's no slope in scope. That variable is not accessible. It's not defined. So it could just be a global variable, but that's not going to work very well because we will later want to go and estimate these variables. But this would work if you just wanted to simulate data. They could also be arguments. So now my model becomes a function from these 3 parameters to a probability distribution over lists of points. And I think this would actually work pretty well if you were building a framework for maximum likelihood estimation. I would do this. I would say that models are functions from their parameters to the data that they want to generate. But I'm not. I'm building a model for Bayesian inference.
That's a quick question. Sorry.
Sure.
In the previous slides, I kind of thought that this monadic approach would mean that either it's got an analytical way or it's somehow automatically choosing the sampling way that it conflates all of these distributions to produce the distribution at the end. But this seems to suggest with the repeat 100, are you now saying is it simply taking 100 samples? Or is there a bit more to it than that? I suspect there is, but...
I mean, it is in a certain way. I mean, it's building a... yes, this is a very... When you're just looking at generating data, it is a very simple interpretation. And it is just, I mean, it's not taking 100 samples. It's building a probability distribution over 100 samples.
Okay, so it's creating a pseudo data set with 100...
It's creating a new probability distribution over those data sets. It's not really sampling anything. You need to sample from this because it ends up being a probability distribution.
So the 100, so if you were to use this, the 100 is not the number of XY pairs in your pseudo data set. That would come later.
That would be the number of points in the simulated data set.
100.
That would be 100.
I
yes.
see, right. Whereas how it's actually doing the conflating the distributions is not to do with that. That's separate, right? It could do that analytically, or it could do it...
You could have different interpretations of this monad, but here we are actually doing things in a very simple way. And I'll show you that when you estimate, things get more complicated. Yeah. So here we really are just simulating data points. Okay, so one thing you could do for the Bayesian inference is to put these parameters inside this do block. So you pick the parameters first, and then you use them. So now we have a probability distribution over the parameters, which is what we needed to do Bayesian inference for the prior. And this is also a self-contained computation. Right? You now no longer have any parameters. You can just run this. It will generate a slope, an offset, and a variance, and it will generate some data. This particular way isn't going to work because I pick 100 different slopes. I want to pick just one slope and calculate my data based on that. So what we'll do is we'll put these draws of the parameters outside the do block. And then we will pick, so you can read this as a computation, right? You can read this as an imperative program that first generates a normal and another normal and a gamma distribution, and then generates the data here. And so you have a complete procedure here for generating fake data. And this is what we want. This is the final formulation of that.
Is that actually Haskell syntax?
Apart from, sorry, I didn't, thank you. I forgot to say, I've changed the arrows to tildes to avoid confusing statisticians. Because here, the arrow means deterministic assignment. So yes, apart from that, it is entirely Haskell syntax. Okay. However, in the real world, it's not enough just to simulate fake data, right? So we have so much real data out there in the world, and we don't just want to generate more fake data, we want to estimate. And so the question is, how are we going to do that? How are we going to use this procedure to estimate these parameters? And so I should probably now introduce the language that we've developed. It is called BASIC, which is a probabilistic functional programming language. I didn't make this up for the occasion, I promise.
Can I interrupt for a second?
Sure.
In the second slide, you pointed to us how the model was one of these funny functions or monadic functions from parameters to the observable data. So it seemed that you have committed on your previous design where you were accepting the parameters.
No, so this is so as I said, it is not a function. The model is not a function. Yeah, I said it was a funny function. So actually, what you're doing is you're generating those parameters internally in the model. Mm-hmm. So it's actually the model is just a probability distribution over the final data, and it generates its own parameters internally. And I'll show you later how you can change those. Okay. So what we want, so let's say we have the data, the observed data, and we get that somewhere from some database or some other way. We have this in scope. And we've defined this model. So what we want now is a joint probability distribution over the model parameters. By joint, I mean that they are estimated together and that you retain information about the correlations. And that's really important. So here I've actually done that. I've fitted some lines to the data points. And you can see that these lines are not all parallel. So the lines that have the greatest intercepts with the y-axis have the shallowest slopes, and the ones with the lowest intersect with the x-axis, sorry, with the y-axis, have the steepest slopes. And so what I mean by that is if you squint and look sideways, this looks like a bow tie, right? It's wider here, narrow in the middle, wider here. And so when you look at the parameter estimates, so these are the parameter estimates, and every dot is a possibility that these parameters could be, a consistent possibility. And so you see that, I guess I should show you they're probable values. If you see that if the growth, if this y-intercept is high, then the slope must be low. Right? And so this correlation between parameters is really important if you start calculating things from these parameter estimates. And you have to do this if you're doing it correctly. So when we go and estimate the model parameters based on the data, that has to be returned as a probability distribution over something. It cannot be returned as two different probability distributions. If these were returned as two different independent objects, then you would lose that correlation information. So the way we did this, we said, first of all, the first condition is the data has some type, T. In this case, T is lists of pairs of numbers. The model is a probability distribution over that same type, list of pairs of numbers. And we give you then an operator that we have to add to the purely functional programming language called estimate, which takes as arguments the model, the data, and gives you back the parameters. And so the type of the parameters, the type that is given by estimate, is a probability distribution over records. And the names, the field labels of these records are the parameter names. And this is not very, from a programming language perspective, this is weird, because these are record labels, and these are just arguments to functions, really. They were the arguments when you flip the monadic do, the bind operator. This is the argument to that function. So there's some kind of, you need some kind of meta-programming facility to set this. And yet, I'm rather convinced that if you want to do it this way, that if you want to have a procedure called estimate, then you have to return this for using, if you want to use this practically for large models that are much larger than this, you have to do this. You could return a probability distribution over vectors or tuples, but then you would quickly lose track of which index is which parameters when you have a large model. And also, remember, some of these models are nested. So some of these parameters that are estimated come inside lists, and you want to keep that information.
So, what is the representation of prob here? Is it like a set of samples?
Yeah. Okay. Good question. So I showed you earlier a definition for prob, which was a program, yeah, that's right. And that doesn't actually work practically. So let me find it. Where were we? Here we are. And let me see. Maybe I can just go out of here. Where were we? Here. So actually what you get is, for practical purposes, you actually need to have a second representation for probability distributions, which is a set of samples, and then that becomes a set of A's. And that you have to do that to do efficient manipulation of the output of estimate. Okay. Okay. And so you can ask for this value. You can ask for it at the console. And so for those of you who know Haskell, you can say that it has a show instance. And so when you ask for it, you get it sort of gets displayed as a record of probability distributions. But that's just a way of typesetting. I mean, it's very difficult to show the user in textual form a multi-dimensional probability distribution. So for that summary, when we output it at the console, you just get the mean and the standard deviation. But in this parameter is retained all the correlations and all the skew and all. This is just a summary. But notice how there aren't any acronyms in here. And all we are doing is getting the parameter estimates. And we're trying to do data analysis just by doing the parameter estimates. Nothing else. Yeah.
Why is slow growth and variance different from, say, inflation? What if my model takes another parameter outside of the repeat, but that's not it shouldn't be a parameter, but it should be part of the model. So how does it know what I want to get out as parameters and what I want to keep inside the model?
Yeah, because this is observed. Yeah. So your data is a list of pairs of numbers. And so this is observed. Both of these two are observed, and they help to shape the likelihood function by being observed. The fact that this is observed actually adds no information to the likelihood. It just changes the offset because this has no further parameter. It's in the data.
Like return.
Yes.
Or pass through a deterministic function and then return. Or pass through a probabilistic function.
Okay, good question. So this does not work for every single function, every single model you can work. Because we're doing Bayesian inference, there are restrictions on what you can do. So what we say is that the data, the final observation has to be a simple combination of draws from probability distributions. And what we mean by simple combination is that it is either a direct draw from a probability distribution, or it is a pair or some other constructor that's built up. Yeah, any kind of constructor. But so we don't support that you do arithmetic operations on it. That would in principle be possible. So you could do any invertible function you can do, you could in principle apply here. But we haven't done the facility for doing that. Yeah.
In principle, you can imagine a situation where you've got quite complex, multi-components of the model with things depending on other things, and all of your data might consist of, combinations and ratios between and so on are things in that model. And as long as you supply enough data to sort of, given the data that you supply, a bunch of these things will drop out as being in the data.
That's correct.
And those that are left, you say, well, they must be the parameters to be.
Yeah, that's correct. So actually, I've lied. I'm sorry. I wasn't going to make it come. Gosh, we actually have to finish soon. This isn't necessarily true. This restriction that these two have to equal can be loosened, and that can be used to great effect if you're doing practical inference. So for instance, if this is a list of records, then you may not want to, and so this may be about people, and one of those records might be the name. And I don't want to build a statistical model for people's names. So you might this record might be smaller in some sense. And then you can run this. So there's a special relationship between these. We call it that they have to be structurally similar. And there can also be too much information in the model, and then that becomes unobserved, and it becomes estimated and becomes a parameter of the model. Yeah. So I'm going to have to make some hard choices about what I want to say now. OK, I'll do this very quickly. So one of the most, for me at least, beautiful consequences of taking this monadic view is that you see some things that are very powerful by looking at correspondences between functional programming and statistics. So it turns out that autoregression equals unfold M. So unfold is a classic combinator from functional programming. It allows you to build lists. So you build lists of A's by having this function which takes an accumulator which is not in the final list. And for each step, it generates a new A, and that's the one that gets put in the list. And it keeps track of this accumulator throughout time. And you can use this to build up lists in various different ways. Here's a complicated way of counting to 10. And here's an even more complicated thing where I'm incrementing the difference between lists over time. Why would you want to do this? Probably because you've been asked to for your first year computer science homework. I don't know why else you would want to use this. But it turns out for statistics, this is really powerful.
In that context, would estimating the parameter of the auto-regression be equal to some fold?
Yes. So, look at the monadic equivalent of this. We are, again, building up lists of things in a, in a monad by running a computation in a monad. And you can think of this, when we switch to the probability monad, you can think of this as a hidden unobserved state, which is not in the output. And it turns out that this generalizes time series data analysis. So most of all of the discrete time series techniques, autoregression, ARIMA, GARC, all of the ones, there are a zillion of them, can be written in some way using this unfold M combinator for different instantiations of this function. So, for instance, here's our old friend, sorry, AR1. This can be written using a simpler version of unfold M, where we just iterate over things, and we just look at the previous step, and the next step is drawn from a normal distribution, where the mean is calculated from this from the previous step multiplied by a constant. If we look at our friend AR2, where we're allowed to look 2 back, we do need the full unfold M. And so the state you're accumulating over becomes the previous step and the previous 2 back step and the previous step. And so the next step is just calculated from a normal distribution, where the mean is calculated by this linear combination of the 2 previous values. And then we return first the next observation, and then the next accumulates a state here. And then that x next becomes x prev 1, x prev 1 becomes x prev 2 on the next step. And so you can write, I don't know if you can write all discrete time series analysis techniques using this way, but you can certainly write a lot of them. And this works with estimate. So then you can then estimate these parameters here. All right, so I'm going to have to skip. So this is what they look like. I'm going to have to skip how we build differential equations into BASIC. So I want to just quickly show you how we use the output of estimate. And so here we have 2 friends here. One is Fmap, which allows you to transform a function, transform a probability distribution by applying a function to every value in it. And so we use this a lot for instance, for if you want to do risk, or if you want to do any calculation based on your parameter estimates, then you can use this function. So for instance, let's say you've got your parameters from estimate here, and that is a probability distribution over records where there's a slope and an offset. And then you want to know if the slope is positive. What's the probability that the slope is positive? And so here we just use Fmap. And here these are then a function which will then be a record, which is a parameter sample. And then you'll just say, is it positive? I'll skip the syntactic sugar that makes this a little bit easier. Second friend that we have here is update. And this is, again, a little bit more magic, and that needs, unfortunately, metaprogramming in this sense. And so here you have update takes one probability distribution, a model, and takes a probability distribution over records that can come from anywhere, and then gives you a new model where the parameters are changed such that they come from this probability distribution. So for instance here, what I can do is, if I've estimated some parameters, I can take the model that I've estimated the parameters for and update that model with the parameters that were estimated. And that gives me what's called the posterior predictive. That is the probability distribution over fake data sets that have been generated using the model and using the parameters that have been estimated from the model. So this is a very nice technique for using for checking your model. So what you do is you sample some fake data, in fact, lots of it, and then you try to probe ways in which the real data is inconsistent with the probability distribution over fake data sets that have been generated through your model and through the parameter estimates that come from the estimation of the real data.
Very quickly, Tom. So that fake data there, that would look like the data.
So that would have exactly the same
So
type.
it's a sample, it's not distribution, and then
No.
then you could then go on to repeat these two.
Yeah, you could actually. Oh, sorry. You could then compare this directly without sampling from it. So you could then
so
use
now
it.
you could do estimate my model fake data, look at the pars 2, and compare pars 2 to pars, and see whether.
You could do that.
And see whether you get an unbiased estimate. Of the
You could do that. You could do that. Yeah. All of those things would be possible. Yeah. Let's skip the way in which there's no escape from uncertainty. So let me just quickly show you how this will be the last bit. So how we've built a platform around this. And so what we've done here is we've built an environment in which you write basic code. Let me show you the document that I generated here for these talks. So what you do is you first of all, you have an editor where you can write code here. And what you mix English language written in Markdown, like hello world, with code. But then you also then have questions. And so some of those questions could be the probability distributions. Here, this is a probability distribution. And so you ask that, and then it shows what I showed you before, where you, well, I'll show you in a second. But some of those questions in this document, which mixes English code and questions, can be plots. And so you can, if we view this, you then get the plot here. Yeah? So this is the plot. And this plotting library, I'll show you that in a second, has been written, this code here, the way that these plots are defined has been written to understand probability distributions. So you can plot probability distributions. So here is, let's see, have I got a really simple one? No, I do not have a really simple one. But so here's the output. Here I'm plotting one of the parameters from the estimation. But you know what, I could also, I could also just plot a probability distribution. So I can just type this plot normal 0, 1. And I get that probability distribution typeset as a histogram. Now, so then you over here on your left, you've got data. So you've got various different kinds of data sets that you can visualize. And then you can do plots of them, which is all very nice, doing scatter plots and histograms of your data sets. But the key thing here is that we've tried to make it easy to build models. And so there's sort of a GUI, a wizard-like thing here for building models. So I believe that this is somewhat similar to something you're working on. And so I can here build, I didn't even know the back button works, but it does. You can build here, let's say now I'm building a linear regression model for this data set. And I am going to say that the output is predicted by the capital here. And so I can set my priors here, and let's see if this works. And so now I can just change my priors here for these values. Oops. And change them around and stuff. And the gamma is always fun to play with. So you can see here how, oops. So as I change this around, yeah, so now I get something that's slightly different. I can just drag this around. Let's do this one though. And now I can do various different things. I can insert some tests. So there would be like saying, is the slope greater than 0 or something like that? And I can do various plots. And now I can then just paste the code for defining all of this that I want to do. And let's do some plots. Let's test whether this is true. And then I paste this into the document that I was working on before, and this is now running. This will be at the end. And so here's the code for the model that I've built. Here's the test. Here's the test. It's greater than 0, 99% sure that this is right. And then here are some of the plots. So data plus fit. And so this code is generated by clicking through a GUI here. Let me see if I can get back to the talk. Yeah, okay. So let me just say that the graphics here that we've done is we've built a plotting library for this, where we've used Angular and AngularJS and D3 to create our own HTML plots. This is really nifty. So you can just define a plot here in the HTML code, just by these extensions, plot extensions that we've used. And so we go through this. This is called Radian. It's open source. And so the way this works is that we've defined, in the basic language, we define plot combinators that correspond to various different things. And you can then nest these plots arbitrarily the way you want to. Let me skip that. In fact, let me just jump to thanking some people. So Ian Ross built lots of this. Jarrett Tobin is working on some of the Markov chain styles. And so with Beat, we're building Beat Ortega is a practicing psychotherapist, and we're building some facilities for calculating changes in his patient's mood and fitting random walk models to that. It's a lot of fun. And let me thank the people at Leicester University who have helped with the project, and Henrik, who is on the board of the company. Thank you.